Constant Speed Propeller Part 2, The Mechanics of a Constant Speed Propeller. Hi, my name is Carl Valeri, and I blog at expertaviator.com. This is the second in a series of videos discussing constant speed propellers. In Part 1, we discussed the purpose and the operation of a constant speed prop. Today, we are going to learn the mechanics of how the propeller works. If you haven't done so, I encourage you to watch Part 1 of this video. There'll be links to where you can find that video, or you can go to expertaviator.com and find it there. A transcript of this video, along with links to suggested reading, is also available as resources used in this video, and you can find that at expertaviator.com also. So no need to take notes, sit back, relax, and enjoy the show. Why the constant speed prop? As a review from Part 1, the constant speed prop is a device which allows us to efficiently convert power from the engine into thrust. Remember, a constant speed propeller is attempting to keep the engine at a constant RPM by adjusting the blade angle and therefore the pitch of the propeller. The propeller pitch is the distance in inches which the propeller would screw through the air in one rotation. When changing the blade angle, we change the pitch of the propeller and use the term controllable pitch propeller. Therefore, when we change the blade angle, we are changing the distance the propeller would screw through the air and are controlling the pitch of the propeller. Therefore, we call them controllable pitch propellers. It really is a simple operation to control the RPM of the engine if you simply think about the blade angle and the results of the changing the blade angle using the propeller control in the airplane. First, we have an engine which converts its power to turn a large shaft which is attached to the propeller. This turning or rotational force is called torque. When you open a jar of peanut butter, you're converting energy from your muscles into rotational force, or torque. The amount of torque depends on the size of your muscles and the tools you use to open the jar, such as a plastic jar opener. If you have a very large jar of peanut butter, you may need to use more torque to get the jar open. In much the same way, if you have a large propeller blade angle, you'll need much larger force to turn the propeller through the air, which is producing resistance similar to the lid on the jar. We can't just see the air with our eyes, but we know it's there. If you reduce the blade angle of the propeller, there's less resistance, less torque needed, and the RPM of the engine speed will increase slightly. Now, if you increase the blade angle, the amount of torque needed increases and the propeller slows, causing the engine to slow down or decrease the RPM of the engine. The propeller in flight is constantly changing pitch to keep the selected RPM setting we choose for our conditions of flight. For instance, we would want a low pitch setting so that the engine can produce the highest RPM during takeoff and go around, but in cruise flight we would want to set the propeller pitch higher, therefore reducing the RPM, thus reducing the fuel burn and decreasing the amount of slippage. And for a description of slippage, you can view Part 1 of this series on constant speed propellers or go to the website. Okay, changing the propeller pitch. To do this, I'm going to use one of my favorite free brochures from Macaulay Propeller Systems. There's a link to this brochure at expertaviator.com, and I highly recommend you keep it for future reference. Another great reference is Rod Machado's Private Pilot Handbook, where Ron's wonderful illustrations make it easy to understand complex topics. The propeller uses a device called a governor to maintain the speed of the engine through varying the blade angle and pitch of the propeller. A governor is a mechanical device that controls the speed of the engine by varying the pitch of the propeller to match the selected RPM. Before we learn how this governor changes the blade angle of the propeller, and therefore the pitch we need, to first learn how the propeller angle is moved. Also, to further simplify our discussion, since changing the blade angle directly changes the pitch, I will use the term pitch to mean changing the blade angle for the remainder of the discussion. Again, anytime we change the blade angle of the propeller, we are changing the pitch of the propeller. Furthermore, we will be discussing propellers used on most general aviation airplanes, which are non-feathering. Look for a discussion on full feathering propellers in an upcoming episode. So first, let's look at the forces acting on the propeller and our constant speed propeller. As the engine rotates the propellers, since it's not fixed, there is a twisting force called centrifugal twisting moment. This makes the propeller, this twisting force, go to a low pitch if it wasn't attached to anything else. But the propeller is attached to something, which allows us to move it and overcome this twisting moment. To move the propeller blades, we attach each blade to a piston inside a dome containing oil. The linkage between the piston and the propeller is called the actuating link and is attached to either end using pins. When the piston moves, the actuating link then moves the propeller. To increase the pitch of the propeller, oil is pumped into the dome, creating more pressure, which then moves the propeller. Now, to decrease the pitch, oil is simply drained. Additionally, there are two forces which move the piston towards the front of the dome: spring resistance and centrifugal twisting moment of the propeller. The first force is produced by a spring attached to the piston. The spring is designed to push the piston towards the dome and is thus forcing the propeller to a low pitch setting. The second force is caused by the turning propeller. The turning propeller causes a twisting moment of the actual propeller itself, which moves the piston towards the front of the dome also. Therefore, when oil is pumped into the dome, it moves the piston away from the front of the dome, overcoming these two forces. One force is a spring. The second force is centrifugal twisting moment of the turning propeller. When the desired engine RPM setting has been reached, a state of equilibrium is reached where no oil is pumped into, nor is any oil drained from the propeller. If any condition of flight changes, this equilibrium, such as if we push the nose down, increase the airspeed, the RPM of the engine will begin to increase, and the governor causes the system to pump more oil into the dome, thus increasing the pitch of the propeller. Understanding the mechanics of a constant speed propeller is easy once you can understand the basic concepts of how the propeller works. I have found most people must review this material multiple times to understand the concepts thoroughly. I encourage you to review this video again and envision yourself using the propeller control system. In the next section, I will discuss the system which pumps the oil into the dome and how the propeller governor works. I also will be discussing some abnormal system operations, such as what will happen if you lose oil pressure or the engine quits running. I also will discuss cold weather operations and running up the engine prior to takeoff. I hope you've enjoyed this video and has helped you understand how a constant speed propeller works. Hope to see you again soon, and look for another video on the mechanics of the constant speed propeller. Safe flying.